Morning. The brave few who are enduring. It's thinning out, isn't it? First of all, office hours are going to be at the Student Learning Center today from 1 to 2. And that's where I'll be holding office hours on Thursdays from now on. I think that worked out pretty well. There's big tables, chance to meet with people a little easier than the roulette of possibly not getting a table at the cafe. It's been brought to my attention that the scatterplot is not loading in problem set 7 correctly. I hope I can fix that this afternoon. Didn't used to be a problem. Are there any questions about anything before we get going? Yeah. Thursday, the walkout. Okay, so let me, what's your feeling about that? I mean, just as a group, you really? Seriously, I mean, it's like, I mean, I know that, you know, everybody would love not to come to class on some level, but presumably you're also here to learn. And I mean, I don't want to feel that I'm shortchanging you guys. By the same token, I think that it's not okay to cut my salary by 10% and expect me to do the same work. So, how many of you think that the walkout is an appropriate thing to do and you're okay with it? How many of you think that it's not an okay thing to do and that really I should just suck it up? A few, yeah. I think that I think I'm going to act in solidarity with other professors and not hold class next Thursday. That's the 24th, right? That's the. I think the reason that it's happening that day is that it's the first day of class that is common to all of the UC campuses. And so this is being coordinated all across the UC system, basically a faculty walkout to protest the way that the budget cuts have been handled and the lack of faculty input or control or some combination of the two over how funds are being reallocated to deal with the budget shortfall. Okay, so not wanting to shirk my job, but by the same token feeling like it just ain't right. Other questions? Okay, we were talking about errors in regression last time, and there were several different meanings of the word error that we were teasing apart. The residual plot is a great tool for figuring out various kinds of errors. So for one thing, what the residual plot plots is the error in estimating a point by the regression line. So it looks at the y value of a point, subtracts the y value of the regression line for the same value of x, and then plots that difference, the residual, the error, as a function of x, the independent variable, the variable plotted on the horizontal axis. Now, that gives us an idea of how scattered the points in the scatter plot are around the regression line, because we basically subtracted the regression line from every point. We're looking at the differences. But it also reveals patterns in the original scatter plot that are easier to see in the residual plot than in the scatter plot. It shows heteroscedasticity more clearly. It shows nonlinearity more clearly. It shows outliers more clearly. What else does it do? Well, it can reveal whether the regression line was computed incorrectly, whether there was an algebraic error in the arithmetic, doing the math. And if there was an error in doing the math, that can show up in a couple of different ways. One is that the vertical mean, the y mean of the residuals, isn't 0. If the vertical mean of the residuals isn't 0, something went wrong in calculating the intercept of the regression line. If the residuals have a trend if there's if the residuals tend to just sort of slope up or tend to slope down, and it can be with a curve, but just sort of if there's a general tendency to be higher on one side than on the other, then that indicates that the slope of the regression line wasn't computed correctly. There was a math error. Okay, so far we've got two kinds of errors. The regression line misses the point. That's a residual, right? It's not a perfectly accurate representation of the data. Second kind of error is somebody made a mistake in doing the math calculating the regression line. Third kind of error is that regression just isn't a very good summary of the data because the data are heteroscedastic or have a nonlinear association or something like that. So regression isn't a good summary of the data. We're going to talk about other kinds of errors as well, having to do with errors in interpreting regression. There's the regression effect, regression towards the mean, the regression fallacy, and conflating the association that regression shows with a causal effect. So things can be very strongly associated and yet one doesn't cause the other. They can either have a common cause or simply both have a trend for completely unrelated reasons. So we were looking at regression, residual plot for the other data we looked at before, and I wanted to get us down to a few examples here. So let's do a few of these together. So first of all, can that really be the residual plot from a regression line? No. Okay, something went wrong. If somebody says this is a residual plot, you say, well, you computed the regression line wrong. How do we know that? Okay, the vertical point of averages, right, is at nearly 100. If the regression line were computed correctly, the vertical coordinate of this would need to be at 0. Horizontal coordinate could be anywhere. The vertical coordinate needs to be at 0. The mean of the vertical residuals has to be 0 if the regression line is computed correctly. What else do we know? Well, generally, these things kind of slope up. There's kind of a trend to the residuals, right? Sort of higher up here on the right, lower down here on the left. I always get, is that my right? Is that my left? Okay. All right. So there's this trend in the residuals, and as a result, that's also evidence that the regression line wasn't computed correctly. What else can we see from this plot? Well, there's a nonlinear pattern, this kind of vaguely S-shaped. Yes? If we fit a line over here, it would slope like that. We put a line here, it would kind of do that. Fit a line like here, it would kind of do this. Right? It's not one general trend. As a result, there's a nonlinear pattern. So the original scatter plot had nonlinear association. What else? Well, the scatter in vertical slices over here is pretty small. The scatter in vertical slices over here is pretty big. There's heteroscedasticity. So from this residual plot, we see that the residuals have a non-zero mean. The residuals have a trend. The data have nonlinear association. The data are heteroscedastic. Okay, regression is a poor summary of the data. Why is regression a poor summary of the data? Is it because there's a trend in the residuals? No. Why is regression a poor summary? The association is nonlinear. So trying to summarize the association by something that is purely linear is not a good summary. And there's heteroscedasticity. And typically, regression is not a good summary of the data when the data are heteroscedastic. OK, so the regression is a poor summary of the data because of the nonlinearity and heteroscedasticity. And the regression went wrong. The evidence that the regression went wrong is not the nonlinearity and heteroscedasticity. The evidence that the regression went wrong is the fact that the residuals have a non-zero mean and a trend. OK, so if the residuals have a non-zero mean, the regression went wrong. The residuals have a trend, the regression went wrong. Somebody computed something incorrectly. Okay? Those two things can be true, and yet regression could be a good summary of the data, right? If it were still basically a football-shaped scatter plot. So it might have been an appropriate thing to do to calculate regression. It just wasn't done correctly. An error was made. Okay. Let's reload this again. Okay, so here, the mean of the vertical residuals is negative, right? It's at about -10, so the regression line wasn't calculated correctly. The residuals have a very strong trend. The regression line wasn't calculated correctly. Things are nice and linear. Right? There's no evidence of nonlinear association, but there is some heteroscedasticity. The scatter over here is pretty small compared to the scatter here in the middle. Many times bigger. So regression went wrong. Regression went wrong. Regression is a poor summary of the data. Let's look at another. Okay. E, all of the above. No. Not E. Everything but E, in fact. All right. Okay. Can everyone see that the residuals have a trend? Okay. It's a nonlinear pattern, but overall, lower on the left, higher on the right. If you fit a line to this, the line would slope. It wouldn't be a horizontal line. Okay, same kind of deal. Let's see if we can get something a little bit different. All right. Do the residuals have a trend here? People prefer to be on the floor? Is it more comfortable than chairs? If I tried to represent this with a single line, where would that line be? Yeah, it'd be a horizontal line right around here. Yeah? Okay, it wouldn't slope up or slope down. So the residuals don't have a trend. But the mean of the residuals is, the mean of the vertical residuals is positive. It's pretty big. So the residuals have a non-zero mean, but the residuals don't have a trend. There's some evidence of heteroscedasticity and very clear evidence of nonlinearity. Yes?
Could you define a trend?
Yeah, it's generally, define a trend. Really what it means is if you computed a regression line for the residuals, if you took the residuals as data and you did regression on the residuals, would the regression line be horizontal or not? If it's horizontal, there's no trend. If it tilts up or tilts down, there's a trend. Okay, so generally speaking, it's like, is there a tendency for the y values to be lower on the left than on the right, or lower on the right than on the left? Notice if you computed the correlation coefficient for the residuals, is the correlation coefficient 0? If it's 0, no trend. Otherwise, there's a trend. So here, there is a bit of a trend to the residuals as a result of possibly nonlinearity, possibly the heteroscedasticity. But, tilt up a little bit. Okay, definitely a trend to the residuals. Yep, tilts up. Okay. But mean of the residuals is 0. Vertical mean is 0. Yes?
So what does it mean if residuals have trends? Like, does it mean like the regression line fits, or?
It means that whatever was subtracted from the data to produce this residual plot wasn't really the regression line. There was an error in calculating the regression line, because when you subtract the regression line from the data, the slope of what's left should be 0. What's left should not have a trend. So the fact that there is a trend here indicates that there was an arithmetic error in calculating the regression line. What was subtracted from the original points wasn't really the regression line. It was some other line.
We can think the regression line doesn't fit in there, right?
Well, it's the nonlinearity that's showing us that even if you computed the regression line correctly, it wouldn't fit the data. It would have systematic differences from the data, because down here, things would be systematically too small. Here it would be systematically too high. That's from the curvature. But the fact that the residuals have a trend is saying when somebody did the arithmetic to try to calculate the regression line, they blew it. They didn't get the math right. So what was subtracted from the scatter plot here was some line other than the regression line. It had the wrong slope. Because if it had had the right slope, then what's left wouldn't have a trend. Questions?
When do you know if it's a good summary of the data or not?
Well, if you have nonlinearity, heteroscedasticity, or outliers, regression's not a good summary. Okay, so basically if you have a football-shaped scatter plot, then regression is a good summary of the data. That's basically it. Yeah. Other questions? Basically, the way I'm using these words, is if you have a football-shaped scatter plot, then you can summarize the scatter plot pretty well with 5 numbers: the means of x and y, the standard deviations of x and y, and the correlation coefficient. With those 5 things, you could sketch roughly what the scatter plot looks like. You wouldn't need to know anything else. Once you have heteroscedasticity, outliers, or nonlinearity, that's not enough information to sort of reconstruct the scatter plot even as a sketch. Right? If you have heteroscedasticity, well, where is it? Is it on the left? Is it on the right? Is it in the middle? How much is it? So forth and so on. It's not captured by those 5 numbers. Right? Similarly, if you have nonlinearity, where is the line systematically below the data? Where is it systematically above? You can't tell that from just those 5 numbers. Right? Other questions? Okay. All right, so we know that the regression line doesn't perfectly pass through all the data unless, except in the very special cases that the correlation coefficient is plus or minus 1. Other than those very special cases, the line misses at least some of the points. Well, how far off is the line from passing through the points? Well, we're trying to come up with a single number that summarizes how much the line misses the points. Well, we have a tool for summarizing the size of a list of numbers, the typical size of the elements of a list of numbers, namely the RMS. So we could look at the RMS of the residuals. We have, okay, the line missed this point. It was too low by that much. It was too high by this much over here, too low, too high, et cetera. How do we summarize overall the size of those errors, the size of the residuals? The RMS is one way to do it. Well, you could go through and calculate for the regression line what is the RMS of the residuals. What would you be doing? You'd be calculating this quantity, the square root of 1 over n times the sum from I equals 1 to n of yi minus axi plus b squared, where a is equal to what?
R times
Right? And b is I'm gonna cheat and just write a times mean of x since we've already defined a. Yeah. Okay, is that right? Right. What is b is the mean of y minus a times the mean of x, where a is this. Okay. So we could go through and calculate this, right? We could look at the scatter plot. We have our list of pairs that are, x. I don't want to well, right there, but we've got, x, I, y, I from I equals 1 to n. That's our n pairs of data. We could calculate the slope, calculate the intercept, subtract the prediction of the regression line from each of the data, sum that to get the residuals. This is the ith residual, ith vertical residual. Square them, average them, take the square root of the result. That's the RMS of the residuals. Okay? Long, complicated process. It turns out, algebraically, that what you get is numerically identical to this. Okay? If you do this calculation, what you get is the square root of 1 minus r squared times the standard deviation of y. Okay. So this is a shortcut for doing that work. All right, the derivation, if you care about it, is there in the chapter in a foot. Yeah, if you click that, you'll get a mess that you probably don't want to see, but just to give you an idea of the algebra. Okay, so that's what we're not going to do. All right, but let's look at this formula. So just heuristically, what's going on? Well, when you subtract the regression line, you shouldn't end up with more scatter in y than you had to begin with, right? If you looked at the you have some cloud of points, and let's say here's the regression line. If I looked at the difference between each value of y and the mean of y, and I squared those differences, took the RMS of those differences, what's the RMS of the difference between all the values of y and their mean? Okay, I'm going to take each value of y minus the mean of y. I'm going to square it. I'm going to sum the squares. I'm going to take the average of that. I'm going to take the square root of that. Yeah, that's the definition of the standard deviation of y. Right? So if from each value of y I subtracted the mean of y, took the RMS of those deviations from the mean, that's the SD of y. Okay. Now, here, if the regression line isn't horizontal, if r isn't 0, then over here, these points that are the points that are down here are closer to the regression line than they are to the mean of. So if I take a point here, it's closer to the regression line than it is to the mean of y. I draw a horizontal line at the height equal to mean of y. Okay, it's going to be closer to this point on average. Some points up here might be closer to that, but on average, I'm going to be closer to the regression line than I am to the mean. Similarly, over here, on average, these points are going to be closer to the regression line than they are to the mean of y. Okay, the regression line does something, right? It explains some of the data. It accounts for some of the variation because there's association. So if I put a horizontal line here, the RMS of the vertical residuals from a horizontal line that goes through the point of averages would be the standard deviation of y. But now if I adjust the slope of that line to try to fit the data better, remember this is the least squares line, it tries to minimize the sum of the squares of the residuals. If I tilt the line to account for the data better, then the RMS of the residuals from that line ought to be smaller than the RMS of the residuals from a horizontal line. Right? It helps. Yes? So what I get if I take the RMS of the residuals from the regression line ought to be smaller than what I get if I take the RMS of the residuals from a horizontal line through the point of averages. If I took the RMS of the residuals from a horizontal line through the point of averages, I would get SDY. That's exactly what it is. Okay? So the answer I get for the RMS of the residuals from the regression line should be less than SDY. Well, what are we doing here? We're taking SDY and we're multiplying it by something. What are we multiplying it by? Well, r squared is between minus 1 and 1. R is between minus 1 and 1. When we square it, it's between 0 and 1. So we're subtracting something that's between 0 and 1 from 1, which gives us a number that is between 0 and 1. So we take the square root of a number that's between 0 and 1. That gives us a number that's between 0 and 1. So we're multiplying s dy times a number that's between 0 and 1. If r is equal to 0, that corresponds to the regression line being horizontal. If r is 0, the regression line really is this horizontal line that goes right through the point of averages, and the RMS of the residuals is exactly s dy. That's what the formula gives also, because if r is 0, r squared is 0, 1 minus r squared is 1, square root of 1 is 1, and we just get s dy. Now, if the points all lie exactly on a line, then all of the residuals are 0. And if you take the RMS of a list that consists entirely of zeros, you get 0. Right? It fits perfectly. There's no scatter around the line fits everything. But what happens if r is plus or minus 1? If r is plus or minus 1, then r squared is 1. 1 minus 1 is 0. Square root of 0 is 0. 0 times s dy is 0. It says that the RMS of the residuals is 0 if the regression line, if the correlation coefficient is plus or minus 1, which is what you expect because all the points then lie on the line. There's no scatter. So what I hope I've just done is convinced you heuristically that this behaves kind of the right way. It's different from proving to you that it's the right answer. That's in the algebra, which I'm not expecting you to be able to reproduce. It's actually, I mean, it's not difficult algebra. It's just tedious. Right? There are things that are, easy and complicated, simple but difficult. There are things that are impossible but easy. Okay. Questions about this? This number, this part of it, the square root of 1 minus r squared, tells you what fraction in the overall what fraction of the overall scatter of y, what fraction of the overall SD of y is accounted for by the regression line. When you subtract a regression line, sort of what's left. This is what's left after you subtract the regression line. So this is the bit that isn't accounted for. I said it backwards. All right. We're not going to go here. Okay, regression effect. This is very important concept. Where this is not a quantitative thing; it's a conceptual thing, and it seems paradoxical when you first see it. But I'll see if I can convince you that it makes sense, and that ignoring it is dangerous. All right, I'm just going to walk you through this example. Forgive me for reading from the book. But let's suppose we have a large group of married couples, and we've measured their IQs. The average IQ for both husbands and wives, this is, post Prop 8, I guess, right? We have 2 gender families. Okay, so the average IQs of both genders are 100. The SD is about 15 points. Let's suppose that the correlation coefficient for these fake data is 0.7. Okay, so generally, the women with above average IQs tend to be married to men with above average IQs. And the women with below average IQs tend to be married to men with below average IQs. This, so far, okay. All right, let's suppose that we've got a woman whose IQ is 150. And try to estimate what her husband's IQ would be using the regression line. Okay? So if you do that, 150 is 50 points above average. We're going to convert it to standard units, multiply by r, and then convert back from standard units. That's the easiest way to avoid confusion. So 50 points is 3 1/3 times 15, right? 15 is the standard deviation. 3 1/3 times 15 is 50. So this is 3 1/3 SDs above average. So it's 3 1/3 in standard units. So we would predict that the husband's IQ is R times 3 1/3 in standard units. So the SDs of both of IQs for both genders are the same, 15 points. So if we take 0.7 times 3 1/3, it's 0.7 times 3 1/3 times 15 points. It's about 2 1/3 times 15 points, about 35 points. So we'd expect the husband's IQ to be about 35 points above the mean. That is about 135. Okay, not nearly as smart, if IQ means smart, as she is. Okay? All right, so if her IQ is 150, we'd expect his IQ, according to the regression line, to be about 135. All right, well, so let's say here's a guy whose IQ is 135. What do we expect the IQ of his wife to be? Right? 150? Well, his IQ is 2 1/3 SD above average. So if we're using the regression line to predict his spouse's IQ, we would predict that it is R times 2 1/3 SD above, R times 2 1/3 SDs above average. And that works out to be 124.5. Right? So we have a woman with an IQ of 150. We predict that her husband's IQ is 135. But if we have a guy whose IQ is 135, we predict that his wife's IQ is 124.5. How can that be? Right? Well, let's see if we can look at the scatter plot and make some sense of this. All right, so we've got a scatter plot that's, let me beef that up just a little bit. Roughly like this. This point is 100, 100. Yep. I've drawn this in a slightly odd way because it really ought to be, you know, 15 this way and 15 this way as a spread, roughly. I mean, so anyway. All right, so here we go. Here is a woman with an IQ of 150. You know, our axis is somewhere over here. Here's 150. And what are we doing to predict what her husband's IQ is? What is the regression line trying to do? We're, in essence, trying to find the point of average. We're trying to find a point on the graph of averages in this little slice. Okay, if we've got the woman's IQ is near 150, so this is female, this is male, and what's going on here? The regression line is going to do something roughly like that. If we look at the average in this slice, we are going to find that the point is, this isn't drawn very well, but the point is below 150. The point here is approximately 135. The average in that slice will be on the order of 135. Okay, well, so now what happens if I look at the average in this horizontal slice and ask, what's the average here? Well, the answer is the average here is going to be down around here, around 124. And a half, if I'm going to be consistent with what we're doing before. Okay, so 150 is an unusually high IQ, right? Most people don't have IQs that high. Even most men who are married to women with an IQ of 150 don't have IQs that high, right? If you take the average of their IQs, it's going to be less than 150. Okay, now we go back and we say, in fact, it's going to be around 135 in this cartoon. So now we go back and say, okay, we have a guy whose IQ is 135. Well, 135 is also above average, right? There aren't, you know, the bulk of women's IQs in this group are below 135. If we ask what's the average of the IQs of all women who are married to men whose IQs are 135, that average is going to be below 135. By how much? By a factor of R, basically. But it's the amount. If we would predict that the spouse's IQ is on the same side of the mean, but closer to the mean by a factor of r. Okay, so if a woman has an IQ that is very far above the mean, 50 points above the mean, we would expect, because the association is positive, that her husband's IQ is also above the mean, but not by quite as extreme an amount. Okay? Similarly, we have a guy whose IQ is above the mean. We would predict that his spouse's IQ is above the mean, but not by quite as much, closer to the mean. This is called regression towards the mean. Okay? Now, what do we predict the IQ of the wife of a man whose IQ is 150 to be? You have a guy whose IQ is 150. What do we predict his wife's IQ to be? It's going to be 135 and a half also, right? This problem is completely symmetric between men and women. They both have the same mean and the same standard deviation, and then there's the correlation coefficient. So if the man's IQ is 50 points above the mean, we expect that the woman's would be r times that, which would be 135. Okay. All right. Now, this kind of situation comes up very, very often when you make two measurements on a collection of individuals. So here, the individuals we're talking about are, in fact, couples. So we have a couple. We make two measurements on the couple, a measurement of the husband's IQ, a measurement of the wife's IQ. There are lots of situations where we make two measurements on people, like their height and their weight, or like their score on a midterm and their score on a final, or something like that. So what tends to be the case is that if the association is positive and someone is above average on one measurement, you would expect them to be above average on the second measurement, but not by as much, where as much means not as many standard deviations above the mean. If someone is below average on one measurement and the association is positive, you would expect them to be below average on the other measurement, but not by as much, not by as many standard deviations. Okay, where does this get into trouble? It gets into trouble in a lot of places, but I'll tell you a story that's in here. It has to do with pilot training in the Israeli Air Force. And I don't remember where I first read this. I believe it was in an article by Tversky and Kahneman, who did really lovely research on people's misconceptions of probability and misuse of notions of probability. Kahneman won the Nobel Prize a few years back in economics. So they did a lot of studies on how people don't think correctly about probability, even if they've had training in probability. But this story about pilot training in the Israeli Air Force is they were trying to do a study on whether punishment or reward is more effective in getting people to improve their landings, getting pilots to improve their landings when they're training. So they had a group where after a particularly good landing, the instructors would praise the pilots, praise the trainees. And they had another group where after particularly bad landings, the instructors would chew out the trainees, okay, for doing a bad job. And they looked at what happened, and what tended to happen was after you praise somebody, they tended not to do as well the next time. Whereas after you chewed somebody out, they tended to do better the next time. Okay? And that's clearly evidence that praise hurts, certainly doesn't help, probably hurts, and that punishment helps, right? They do better. Okay? Except that that's also completely explained by the regression effect, regression towards the mean, right? Somebody does particularly well. They do particularly well by some combination of skill and luck. What makes it extraordinary? Well, probably their luck was good that time. Had skill, but their luck probably added to their performance that time. Well, the next time, their luck might not be as good, and it might subtract from their performance. Whether rewarding them, whether praising them has any effect at all, right? They're still kind of likely to do worse the next time. Similarly, you take them after particularly bad landing. Well, what's particularly bad? Well, it's a combination of luck and skill. They might not have that great skill, but their luck was probably bad that time also. And chances are next time their luck won't be quite as extremely bad, and they'll do better even if you don't punish them. right? So you end up conflating the effect of reward and punishment with the regression effect. So even if nothing at all were going on, even if reward and punishment had no effect whatsoever, you would expect to see that in the data. That is, after particularly good landing, expect it not to be quite as good next time. After particularly bad landing, expect it to be a little bit better next time, assuming it's not so bad that you don't walk away. Okay, so this tends to, many of you guys are going into business and you'll be in situations where you have power over other people, you have underlings, you are getting an opportunity to reward them or punish them for their performance. And then in turn, if you are not at the highest level of management, and maybe even if you are, to be rewarded or punished for what your underlings do. So the story is that by the regression effect alone, you are likely to be rewarded for punishing those underneath you. Because they'll do better next time, even if you hadn't, and then you'll get rewarded, right? Okay, just saying. Okay, so this regression effect comes up a lot, just whenever you have repeated measurements on the same people. Now, it is not an inviolable law that if you do really, really badly on one measurement, you are going to do better the next time, right? You could do worse. So if I look at the people in the class, we look at, say, scores on the midterm, and I look at the people who did worst on the midterm, chances are, all other things being equal, they won't be the people who performed worst on the final, right? Because your performance on the midterm has got something to do with what you know and something to do with luck. What you had for breakfast, how much sleep you got the night before, whatever it was, okay? Now, that doesn't mean you can count on the regression effect to raise your grade on the final, right? Okay, so it doesn't gotta happen, but it tends to happen, right? It tends to happen. Okay. All right. So, are there questions about this stuff? We talked about a variety of different kinds of errors in regression. Somebody want to list one or two of them for me? Computational error, okay. You might just make a mistake in doing the math to calculate the regression line. That shows up in a residual plot in what way? How can you tell? Okay, vertical mean of the residuals isn't 0, that's one way. Or if there's a trend in the residuals, that's the other way. Okay, what's another kind of error that we're talked about in this chapter?
You're not supposed to use regression.
Okay, so regression isn't a good summary of the data. Regression is not an appropriate tool in that particular circumstance. And what are some circumstances where regression isn't a great summary of the data? Sorry, the heteroscedasticity, okay, or nonlinearity, or outliers, okay. And how did those show up in the residual plot? Just like that. They look just like what they are, only more so. Yeah. Okay, so you will see some curvature to the residuals if there's nonlinearity. You will see differences in the vertical scatter of the residuals in different places if there's heteroscedasticity. You'll see outliers in the residuals if there's outliers in the original data. It's sort of if and only if, just bigger. It reminds me that anybody listen to Laurie Anderson? Know her music? She has some. I like her a lot, but he's like, paradise is exactly like where you are right now, only much, much better. Okay. Nonlinearity, heteroscedasticity, and outliers show up in the residual plot, just like in the scatter plot, only much, much better. You can. Okay, any questions? All right, let's take 90 seconds and we'll go on to the next thing, which is a very big change of pace. Okay, let's get started again. All right, we're now, what we've been talking about so far in the class has been descriptive statistics. We're given some data, and we're trying to summarize them in some way, by a chart, by a regression line, by percentiles, by histogram. We've given some data, and we're trying to summarize it, express general qualities of the data. Is it multimodal? Is it unimodal? Is it skewed? Is it this? Is it that? How spread out are the points? What's a typical value? So forth and so on. What we're about to dive into is probability. We're going to build probability from counting. Probability is math. Okay, this is now somehow not as directly connected to the world. We're not given some data. We have a hypothetical situation. We have a model. We have a story about the world. And we're going to do some math with that. What comes after probability is we start mixing the two things together to say, okay, if I knew what the world was like, I could predict what I would see. Right? If I knew everything, if I were omniscient, then I would know, if I reach into this box of numbered tickets and I stir it up and I pull it out and I pull out numbers and I know what all the numbers are in the box, I would have a very good idea of what the averages of the tickets in my hand would be. When we get to inferential statistics, we'll be turning that around to say, okay, I reached into this box in a certain way. I pulled out tickets at random. I saw this value for the mean. What do I know? What can I learn about what's in the box from that? Okay, so first part has simply been, I got this list of numbers. How do I summarize them? What can I, blah. Second part is, suppose we know what's in the box. Can you predict what you're likely to see when you reach in, stir it up, and pull some out? And the third part of the course is going to be, okay, I did that process of reaching in, pulling out a random sample, and looking at it. What can I say about what's in the box? All right, so we're going to talk about counting now. Counting is surprisingly hard. And this is true at all levels. I mean, almost invariably, when I make a programming mistake, it's because I've miscounted an index in some loop or something like that. It's just hard. Now, so we're going to look at strategies for counting things, especially for counting very large numbers of things, and come up with some strategies that work in a variety of circumstances. In any particular problem, you're going to have to figure out which one's going to work for you, right? But these are some ways to approach it. So let's talk about tossing 3 coins that are distinct, let's say a penny, a nickel, and a dime. And we want to look at all ways that those 3 coins can land. Now, first of all, we're going to ignore the possibility that the coin lands on its edge or that a bird swallows it while it's flying by in the air or something like that. Okay, so the coins are going to land. All right, so what could we have? First toss could result in a head, second toss in a head, third toss in a head, right? Or we could have first toss tails, second heads, third head. In all, there's 8 possibilities. Where's the number 8 coming from? How could we jump to the end and know that? Well, it's 2 cubed, right? So where's the 2 cubed coming from? First thing has 2 branches. Could get heads, could get tails. Regardless of what happens on the first toss, we get 2 branches. Regardless of what happens on the second toss, we get 2 branches. Okay, so we end up with 8 in all. 2 times 2 times 2. Branch, branch, branch. Okay? Generally, if we have something that involves a sequence of choices where the number of choices that are available to you at a given level doesn't depend on which choice you made at the previous level, you can find out how many leaves there are on this upside-down tree by just multiplying the number of choices that you have at each point. In this case, you have 2 choices for what happens the first time. Regardless of what happens, regardless of which node you end up here, you have 2 choices for what happens in the next level. And regardless of which of those nodes you end up at, you have 2 choices for what happens at the level below. So you end up with 8 possibilities in all. Okay? So this is an instance of what's called the fundamental rule of counting. Let's look at a different example. This is actually a little bit sad. The names here were not chosen at random. These are all statisticians. They're all statisticians in our department. Betty Scott died during my time in the department. Eric Lehman, a gentleman and a scholar, absolutely wonderful human being. He just died about a week ago. His wife is Julie Schaefer. Jersey Neyman is the founder of the department. Lucien Lacam died a few years back. I mean, anyway, these are all important figures in statistics and probability, and they're yeah. Okay. At any rate, let's suppose that we have 3 men and 4 women, and we're trying to make pairs, 1 man, 1 woman. Okay? How many possible ways are there of doing that? Well, one way to conceptualize this is to think about first picking one of the 3 men, and then picking one of the 4 women to pair the man with. Okay? If we do that, no matter which man you pick, no matter which of the 3 you pick, you have 4 choices for the woman. So you can write this as a tree where the first branch, there's three branches off the root, and for each of those 3 branches, there's 4 more. There's 4 leaves. Okay? So fundamental rule of counting says that the number of things you ought to get is 3 times 4, which is 12. Well, what would happen if we first picked a woman and then picked a man to pair the woman with? We would have 4 branches from the root, and then each of those 4 branches would have 3 leaves. There would still be 12 leaves. We would still get the same answer. It doesn't matter which way we conceptualize making the choice. What matters is that we conceptualize doing it in such a way that the number of leaves off a given branch is the same regardless of which branch you take at the first level. Okay? Now, suppose that Eric and Julie would not agree to serve on the same committee. Okay? Then we can't find the number this way, because if at the first stage we pick Eric, then there's only 3 choices for the woman. Whereas if at the first stage we pick Jersey, there's 4 choices for the woman. Okay? So in order for the fundamental rule of counting to work, the number of branches from at each level, the number of branches you go to the next stage has to be the same for every node. Every branch you're on has to split into the same number of sub-branches. Okay, so to summarize this in math, if we have a sequence of trials or of choices, T1 up to Tk, and the number of possible outcomes, the number of things you get to choose among at step T1 is N1, the number you get to choose among at T2 is N2, no matter what you picked at stage T1. The number at T3 is N3, no matter what you did at stages 1 and 2, etc. Then the total number of leaves on that tree as you expand and expand and expand is just the product of the number of choices you have at each stage. Okay? Seems trivial, is in fact incredibly powerful. I'll be using it over and over and over again. All right. Okay, let's do this exercise 9.3. So we have a small company. It has 3 vice presidents, 4 top-level managers, 6 mid-level managers. You want to make a committee that has one of each of those 3 types of management personnel. How many ways are there of doing that? We could think about first picking a vice president. No matter which of the 3 we pick, we have 4 choices for the top-level managers. No matter which vice president we pick and which top-level manager we pick, we have 6 choices for the mid-level manager, right? So there should be 3 times 4 times 6 possibilities. If I type 3 times 4 times 6 in here, it will count it as correct. If I submit that on the homework, it will count it as wrong. I have to actually put in the number. Okay? All right. Now, here is All right, so we've got now one strategy for counting things in a complex situation, namely represent what you're doing as a sequence of choices where the number of choices at one level doesn't depend on what choices you made before. The choices can depend, but the number of choices can't. Okay, so for example, if I talk about, I think there was an example up above. Let's think about dealing 2 cards in sequence from a deck of cards. No matter what card I get the first time, there's 51 choices for the second card. Right? There's 52 cards in a deck. Does everybody here have some experience with cards? 52 cards in a deck. They're in 4 suits: spades, hearts, diamonds, and clubs. In each suit, there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Sometimes in some games, aces count low. In some games, they count high. In some games, they count both. But basically, 4 suits, 13 cards per suit. OK, so 52 cards in all. I deal 1 card. No matter what card I get, there's 51 choices for the second card. It's not the same 51 choices, right? If the first card I deal is the ace of spades, then the ace of spades is not one of the remaining choices. If the first card I deal is the 2 of spades, then the ace of spades is one of the remaining choices. But whether I first deal the ace of spades or the 2 of spades or the 9 of diamonds, the number of choices available at the second level is 51. Okay, so the total number of things I can do if I deal 2 cards in sequence is 52 times 51. 52 for the first, 51 for the second. All right, so that's the fundamental rule of counting. That's a strategy for counting things in complex circumstances. We're now going to look at a bunch of other strategies for counting things in complicated circumstances. Here's one of them. If you can't count the whole thing as a group easily, consider breaking it up into subgroups so that everything is in exactly one subgroup. Then count the subgroups and add what you get. Add the counts. Right? This is, you break something big into pieces, you count what's in the pieces, you add up the totals. Right? Seems trivial, really, really useful. All right, so we just did this example 9.3. Here's another example. The same company wants to make a committee that just has 2 people in it. The 2 people have to be from different management groups. How many committees are possible? Right? This is a good strategy. Break this into disjoint pieces, non-overlapping pieces, so that every possibility is in exactly one of the pieces. Count the results and add them up. OK, so what are the pieces going to be here? Well, if I knew that the group consisted of, that the committee consisted of a vice president and a top-level manager, I could find a number of possibilities like that really easily. It's 3 times 4, right? If I knew that the group consisted of a vice president and a mid-level manager, I could find out how many ways there are of doing that really easily. It's 3 times 6, yes? OK, so a strategy for solving this problem is let's divide all the possibilities up into what kinds of executives are in each of the groups. So we can divide it into those 2-person committees that consist of a vice president and a top-level manager, those 2-person committees that consist of a vice president and a mid-level manager, and those 2-person committees that consist of a top-level manager and a mid-level manager. Right? So we're taking the whole thing, we're breaking it into 3 pieces. Miraculously, there's 3 pieces there. And then counting those separately and adding the result. Okay? So that's the strategy. What do we get? Well, so first of all, are those all the possibilities? Would I have left anything out if I do that? Am I double counting anything if I do that? No. Right. If the committee consists of a vice president and a top-level manager, it does not consist of a vice president and a mid-level manager. Right? There's nothing that can be in more than one of those 3 groups. And every 2-person committee is in one of those groups. So every 2-person committee is in exactly one of those groups. OK, so what's the answer? The answer is 3 times 4 plus 3 times 6 plus 4 times 6. So for each of those pieces, we can use the fundamental rule of counting to figure out how many items there are in the group, and then add the results to get the total. Easy, yeah? Okay. All right, let's do this one. So if we toss a fair coin 3 times in a row, the number of possible sequences of heads and tails, we already know that that's 8. How many sequences have at least one head and at least one tail? Okay, people are saying 6. What are you doing conceptually to get there? Okay, so this is another really good strategy for counting things. What you're doing is you want to know how many things are in here. You're counting the number in some larger set and subtracting the stuff you don't want. This is another basic strategy for counting. You want to know how many are in a group. Count a group that's too big. Subtract the ones you shouldn't have counted. Okay, so what you guys are doing is you're saying, I know that there's 8 sequences in all of heads and tails. I know that one of those sequences is all heads, so it doesn't have at least one head and at least one tail. One of those sequences is all tails, so it doesn't have at least one head and at least one tail. And all the rest have at least one head and at least one tail. So I count a group that's too big. I've got 8. I'm subtracting off the ones I shouldn't have counted. Another great strategy for counting things in complicated situations. Okay. The other strategy, which we'll probably see in a little while, that comes in very handy is the following. You want to know how many things there are in some set. It's very difficult to count. You count them too many times and then divide by the number of times you counted them. Okay, now why anybody would want to do things this way is a little bit hard to see before we get to a particular example, but we'll get there pretty soon. So here the idea is let me give you an example. I want to make a 2-person committee, and I'm going to pick 2 people from the room to be on the committee. So let's say that there's, I don't know, 60 people in the room right now. I have 60 choices for the first person. Given those 60 choices, I have 59 choices for the second person. Are there 60 times 59 choices for that 2-person committee? Is that the right answer? So I've double counted, right? Because, you know, I don't know people's names yet, but you know, if I pick you as the one out of the 60, and then you of one of the remaining 59, that's the same committee as if I pick you first and you second. Because if it doesn't matter, if the roles are interchangeable, right? I'm not picking one person to be the chairman of the committee and the other person to be the secretary. I'm just picking 2 people. So I've double counted. I would need, because I've counted you then you as a different committee from you then you, but in fact you're the same committee. Okay, so I've counted things too many times by a factor of 2. I could take that number, 60 times 59, and divide it by 2. And then I'll have the right answer, because I've just double counted. Okay. We'll see that in action a lot. All right, so let's suppose that we have a collection of items, let's say 5 things, and I want to know how many ways there are of sort of lining them up in a row from left to right. That is your left, yes. Okay, so there's 5 choices for what comes first. No matter what I put first, there's 4 choices for what comes second. No matter what I put second, there's 3 choices for what comes third, etc. So by the fundamental rule of counting, there's 5 times 4 times 3 times 2 times 1 possibilities for lining those 5 things up in an order. Okay? That number, 5 times 4 times 3 times 2 times 1, is 5 factorial. Okay, that's in general, the symbol is, n times n minus 1 times n minus 2, etc., is n factorial, which is n with an exclamation mark. And there's a convention that 0 factorial is equal to 1. Okay, the number of ways there are of putting no things into an order from left to right is only one. Namely, you just don't put them there, right? Okay. All right. So, as an example, this is back in the days when people had CDs rather than MP3 players. Suppose I have a CD that has 13 songs on it. I can program the player to play them in any order I want. How many different patterns of songs can I get? How many different orders can I get? Well, I have 13 choices for the first. No matter what I put first, there's 12 choices for the second, etc. So by the fundamental rule of counting, I just multiply all those numbers up. That's 13 factorial, and it's something like 6 billion. Okay. All right. What if I just wanted to put 5 of the songs in some order? I'm making a playlist of 5 songs chosen from my 13. How many playlists of 5 songs are there? Right. Well, I still have 13 choices for the first, 12 for the second, 11, 10, 9, and then I stop because I'm not picking a 6th song or a 7th song or whatever. Okay, so by the fundamental rule of counting, I've got 13 times 12 times 11 times 10 times 9, and that's 154,000 and change. Okay, now there is a more compact way of writing this. So first of all, we're going to give this a symbol. So NPK is the number of permutations, that is orderings, of k of n things. We have n things in all. We're going to put k of them in an order, to some order. And how many ways are there of doing that? Well, by analogy with this, I have n choices for the first, n minus 1 choices for the second, etc., on down to n minus k plus 1. If you count how many terms there are here, there are k terms. Okay, if I end at n minus k plus 1, there's k terms here. Okay? So this is NPK, but in fact, we can write this more compactly using factorials by noticing that what's missing to turn this into n factorial? If I multiplied it by n minus k minus 1, n minus k minus 2, n minus k minus 3, on down to 1, then this would be n factorial, right? Okay, what is n minus k times n minus k minus 1 times n minus k minus 2, etc.? It's n minus k factorial. So this thing is, in fact, n factorial divided by n minus k factorial. Right? The n minus k factorial cancels all these terms that aren't there. Okay, so NPK is, in fact, equal to n factorial over n minus k factorial, which ought to be blue, but isn't. I'll fix that later. Okay. So, in fact, if you try to calculate this for large numbers, you are far better off using this formula than using this formula, because n factorial could well lead to overflow when the first k terms in that product don't. So very often these numbers will be ginormous, and it's much more stable numerically to calculate it that way than to use this shorthand. But algebraically, I mean, if you didn't have to worry about finite precision arithmetic, overflow, et cetera, they're mathematically equivalent. They're not computationally equivalent. All right. Okay, so the number of possible orderings of n things taken k at a time, k of n things, is npk. That's n factorial over n minus k factorial. And that's assuming that you're taking at least none of them and no more than n of them. Okay? If you can't take more than n of n things, and you can't take a negative number of things. All right. Let's look at this. 9-9. So in Texas Lotto, 6 of 50 balls numbered 1 to 50 are drawn at random by a machine. That's called random sampling without replacement, a simple random sample. It's a model that we're going to use for an awful lot of things. To play the lotto game, you pick 6 of those numbers. If you pick the same 6 numbers that the machine picks, then you win the grand prize. And if you don't, I mean, there are smaller prizes for matching some of them, just like there is in California, et cetera. But so here someone is asserting that there are 50 P6 possibilities for the winning combination. And he, for a certain sum of money, will show you how to improve your odds of winning. All right, so what's wrong? Are there 50 P6 possibilities? What is 50 P6? What does it represent here? What is it calculating? What question has as its answer 50 P6?
What was the question again?
50 P6 is some number, right? Is it the number of possibilities for the winning combination? You've got 50 numbers. Machine picks 6 of them. You pick 6 numbers. If your 6 numbers match the 6 the machine picked, you win. Are there 50 P6 possibilities for the winning numbers, the winning 6 numbers? No. OK, right. It's a leading question, right? I wouldn't be asking you if the answer were yes, right? OK, why not, right? What's wrong? Yes?
The order doesn't matter.
Your order doesn't matter. OK, what matters is which 6 numbers the machine picked, not the order in which it picks them. It's like a hand of cards. You're dealt 5 cards. If you're playing, a game of like draw poker or something, you're dealt the cards. You get to look at the cards. What matters is which cards you got, not that the first card you got was a 2. What matters is that you have a 2 in your hand. Okay, same thing here. It doesn't matter whether the machine picks the numbers in the same order that you pick them or not. What matters is, did it pick the same numbers? Okay, so 50 P6 is the calculation you would do if you cared which number the machine picked first, which picked second, which it picked third, et cetera, et cetera. Okay, but you don't. All that matters is that you get the same numbers. So in fact, the number of winning possibilities is much, much, much less than that. How much less than that? Well, remember we were talking about making a committee from 2 people in the room, and we realized that if we counted, if we take 60 for the first person, 59 for the second, we've double counted because the 2 orderings of those people, you first then you, and you first then you, those are 2 orderings of the same set, the same 2 individuals, the same set of individuals. Well, if I have 6 numbers, if I have a set of 6 numbers, how many sequences of 6 numbers can I make from that? If I ordered them from left to right. Well, from the 6 numbers, I have 6 choices for which goes first, 5 for which goes second, et cetera. So there's 6 factorial ways of taking that set of 6 numbers and arranging it into a sequence of 6 numbers. Okay? So this number, 50 P6, has counted one set of 6 winning numbers, has counted one set of 6 winning numbers in 6 factorial different orders, right? It takes the numbers, says one winning combination is 1, 2, 3, 4, 5, 6. A number winning combination is 6, 5, 4, 3, 2, 1. No, that's the same combination, right? It's the same set of numbers. Okay, in all, those numbers 1, 2, 3, 4, 5, 6 can be arranged in 6 factorial ways. So this overcounts the number of possibilities by a factor of 6 factorial. So we could find out how many possibilities there are by taking that number and dividing by 6 factorial. And that's exactly the strategy I was talking about before for counting. Count the objects the same number of times each, but too many times. And then divide by how many times you overcounted. Okay. All right. That's what we just learned how to do, was to find subsets. So you guys are in a hurry to go. We have 3 minutes. I have to give you every possible minute since we're going to boycott on the 24th, right? Okay, if I take a set of 3 distinct things, I have 3 choices for what goes first, 2 for what goes second, and there's only 1 left for the third. 3 times 2 times 1 is 3 factorial is 6, right? So if I looked at taking a subset of 3 people out of a class of 20, if I take 20 times 19 times 18, that has counted each set of 3 people 3 factorial times, 6 times. So if I want to find out how many sets there are, I could take 20 times 19 times 18 divided by 3 times 2 times 1. The result is called the number of combinations of 20 things taken 3 at a time. Before we were talking about the number of permutations of n things taken k at a time. They're related very closely. The number of combinations is going to be smaller than the number of permutations by a factor of exactly k factorial. So this is n choose k, n c k. It's the number of combinations there are of n things taken k at a time, the number of sets, the number of subsets of size k drawn from a universe of n objects. And it is n factorial divided by k factorial times n minus k factorial. The special case that we were talking about of finding a set of 3 students from a class of 20 students corresponds to 20 choose 3. That's 1140. Okay. All right. I will let you go. Some of you I will see at the Student Learning Center in a little bit.